Recorded is rolling. It is Monday, April 6th. We're going to continue with our review. We're doing rotational mechanics. Right, so by AP's book, they split this up into two units, Unit 5 and Unit 6. Unit 5 is mostly, guys, what does capital I stand for in this class? Inertia. Yeah, rotational inertia. So something about the inertia of things that are rotating. Right, and what is, okay, so it says, how do you read this? Rotational inertia for, say, a point map could be what? Sum of
Mass.
yeah, mass times distance squared. Some of them are squared. This is from the pivot point. Right? How do you read this one right here?
R cross M.
Yeah, so torque is R cross F. Like using a wrench for them. Right, so that's basically unit 5 by AP's book. Also this one. Let's put this one here. Guys, if you have a net torque, that can result in what times what? Yeah, rotational inertia times angular acceleration. Is this like Newton's second law of motion, F equals NA? But now it's for a rotating something. Right? Okay. All right, so that's unit 5. Unit 6 is what is capital L in this class? Angular momentum. Okay, so something is rotating, right, has a momentum in an angular sense, right, rotational sense. I can solve it. Right? And how about this very last line? Yeah, rotational kinetic energy. So what's the energy of rotating? Right, how much work does it take to get something to rotate like that? Okay, guys, what we covered today is these formulas in the top right. Okay, so here's right after the part. Here's linear kinematic. We got some dynamics and gravitation stuff mixed in here, circular motion. Then here's your energy. Here's your momentum. We've covered all that so far. We're going to this rotational mechanics here. Rotational mechanics. Right here, great. Now, so some of these are actually rotational kinematic. I think we covered these already in the review, didn't we? This kinematic stuff, right? Like turntables turning. Guys, I will get you a rotational mechanics quiz later this week. I will see just organically how long does it take to naturally cover all the stuff, but we'll do this review the same way we've been doing it. Give you guys some examples. You guys can figure it out in your notes. It's fun. Back at the end of last week, I gave you guys an energy momentum quiz. You guys remember you had Friday to work on that with each other, open notes, and some of you guys turned that in. If you did, it's already graded. If you haven't turned it in yet, then today would be a good day, and I'll grade those for you guys. Get that for you. Okay. Energy AP Classroom. This was an assignment from last week. Some of you guys did it, but not everybody. So I will check AP Classroom later this week and do an update. All right, so you guys good with what we're doing? You guys good? All right, let's jump into this review. All right, so center of mass. Can you guys come up with a formula for center of mass? Great. It is actually this is a formula on your formula page. It's kind of in a weird place. It's right beneath the 3 kinematic formulas on your AP equation page. Okay. But if you can either know this or have remembered it, or be able to figure it out, if you can figure this out from scratch, then you definitely know it. You know it. Right? Right. So this general box, this gold box, isn't it the sum of mass times location divided by sum of mass gives you the average location? Okay. Now this is along a specific axis. So here you guys see I have an x-axis. If you were working in 3 dimensions, would you have to consider the x-axis, the y-axis, the z-axis? Maybe do 3 independent equations. Figure out the x, y, z coordinate for the center mass. Okay. Let's throw some numbers up here. So I'm going to copy down that picture and just throw some numbers on those masses. If you guys have a ruler, I have a ruler. Let's get an x-axis going. All right, I'm going to call mass A about 7 kilograms. Let's call mass B how about 3 kilograms? And let's say that those are separated by a distance of 10 meters. All right, so what I just said, all right, let's bring this over here. All right, so I was drawing this as I was saying. So let's put 7 kilograms here, 3 kilograms here. Let's say this gap is 10 meters. Okay, hey guys, if you stuck a stick through these masses, like just like that, okay, and you balanced it on your finger, would it balance at the geometric center? No. Would it be closer to the right? No. Would it be closer to the left? Yes. So somewhere over here. Somewhere over here. I'm gonna make a guess. So it's probably right about there. Is the center of mass. Okay. Right, so can you guys calculate that? Where exactly would it be? Where exactly is that? Give you guys a head start. No, I like to give you a head start. So we said center of mass is sum of mass times location, fill subscript i's, divided by the sum of masses. So, hey, we can define this leftmost point as 0 meters. Then over here it could be 10 meters, I guess, locations. So we'll go 7 kilograms at 0 meters plus 3 kilograms all the way out at 10 meters away, and then divide by 7 plus 10, or sorry, 7 plus 3, which is 10. The kilograms. Okay. Oops, sorry, 3. What did I just do? 3. You messed up something.
You didn't multiply that.
30. Yeah, no, you're right. There you go. 3 meters. There you go. That looks a lot better. All right, 3 meters down. 3 meters from the left point, because I define the left point as 0.0. Okay. Does that look like it can make sense? You saw it as multiple choice. Like, oh yeah, that's definitely it. Okay. All right. Are you guys good with center mass? All right. So you go. There's for 2 masses along a single axis. We just did that. All right. We'll make something unstable, neutral, or stable. I don't think AP is going to ask that. That's good to know. Some pictures there. Same thing with this. I don't think AP is going to ask about that. But if you work for NASA one day, good to know that one. Ooh. Now, this is on your AP equations. How to find this. Okay. Here, let's still going over there. If you're in class, you guys see those 2 sticks over there by the wall? Right? They got the masses attached to them. Right? Now, if let's say each mass is mass m, right? It's some distance r from the center, and I'm just grabbing this at the center and rotating. Right? And let's say the meter stick has negligible mass by comparison, so almost all the mass is in that red point and that red point. Okay, it's what would the let's start with in general. Rotational inertia is what? Yeah, sum of mr squared. Right. So there's mr squared. And then you can add up multiple points if there's multiple points. Right? Well, here I basically have 2 points on each of these pictures, left picture, right picture. So guys, what do you think goes right here?
MR squared.
Yeah, this MR squared. But then don't forget about this guy over here. You guys see where the 2's coming from? 2 MR squared. Right. How about this picture on the right?
18. No.
Huh?
18 MR squared.
Yeah.
Right? It's the 2 and the 3.
Right? Because guys, 3 squared is 9, and there's 2 of them. Do you guys see where the 18s are from? Okay. Now, if you compare the picture on the right to the picture on the left, right? The difference is we've scooched each mass 3 times further away. So guys, 3 times further away squared. What's 3 squared? 9. And if you take the ratio of these 2 i's, what do you get? What's 18 over 2? Also 9. Okay. You see functional dependence? Okay, now guys, this table here, you wouldn't be expected to memorize. AP would give you some value, but I think it's good to know some of these anyway. Okay? Like, you guys know a point mass is just very simply mr squared. You guys know that? Okay? Guys, what about a ring that's rotating about its geometric center like that? What does that also have to be logically? Also mr squared, because every single point is distance r from the center. Anyway, that's what a ring is. Now, what if you make it solid all the way through? Now, isn't the mass overall average distributed closer to the center? So is it more or less than mr squared? It's got to be less, right? Yeah, it works out to be a factor of a half. Again, AP would give that to you if they wanted you to solve something with that. I've never seen them ask about this thin coin on the edge, but pretty close to, like, if you spin it, like spin a quarter, this is just spin it right. Well, guys, how about these 2 sticks down here? You guys see these 2 sticks? Now, let's make believe for a moment that these are both the same mass and the same length. Maybe I've zoomed out this picture on the right. Okay. Guys, could these both be the same mass, same length? Okay. Which one of these has more rotational inertia? The one about its center or the one about the end?
Center.
About the center, it's 1/12 ml squared. What if you had this yourself? Guys, what if you take a meter stick? Could that be a meter stick? You grab it at the center, you start shaking it back and forth. Ooh, okay, I feel a little bit of resistance to change of motion. Works out 1/12 ml squared. Now, you scoot it all the way to the end. So now you're holding at the 0 centimeter mark. Does that feel like more inertia or less inertia? I think more. Guys, what number is bigger? 1/12 or 1/3? 1/3. In fact, how many times bigger is that? 4 times. Guys, it's 4 times. Right? Do you think you could start this picture on the left? Do you guys remember parallel axis theorem? Maybe I'll do that with you guys later. Guys, hold on. Maybe this could be a good example for later for parallel axis theorem. If you know one of these, you can get the other. Does anybody remember the bowling ball? It's like 2/5 mr squared. Does anybody remember the basketball? It's being 2/3 mr squared. Okay. But more importantly, you could eventually apply these to equations later on if you remember this. Okay. All right, you guys go with the rotational inertia so far? Oh, here it is, parallel axis theorem. Yeah. Right. What does parallel axis theorem say?
It's like 1.5 to something. It's like it's at itself like 1 or something.
Yeah, okay. Like guys, this basketball is revolving around the central axis. You guys see that? Well, if I go back to the last slide, if it was spinning on your finger, wouldn't the rotational inertia just be 2/3 mr squared? Right? Which is part of what it's doing. It's rotating about this axis, but it's further revolving at distance d. So what you do is you take the original value and you add in d squared. Okay? Is that parallel axis? Guys remember that? In a really common application, if something's rolling across the floor, because guys, is this actually rolling through its center, or is it rotating about this point all the way at the bottom, which is offset from the center, isn't it? So you say, take the table value 2/3 mr squared, but that's about its center, right? And say plus mr squared, and that gives you 5/3 mr squared. Okay. While you guys are digesting that, I'm gonna go back to I'm gonna set up from my notes over here. Set up that stick problem from earlier. Stick problem. Okay. Once you guys see it, this actually works. So guys, if this stick is rotating about this axis right here, okay, rotating like this, but some omega, okay, what has some mass m and some length l, some length l. The whole thing is l. Okay, right, you guys write that in your notes. This stick has some mass m, some length. Actually, I got it right here. I can give you guys a little demo. There it is. That's what I'm doing. So I'm just doing this right here. You guys see that? See that? Okay. Oh, I felt some resistance to change of motion. I felt some rotational inertia. Okay. And if I go from the table for this scenario, it ends up being 1/12 ml squared. Let's say I'm allowed to know that. I'm allowed to know that. Okay. Now what we're going to do is we're going to go through parallel axis theorem. Okay. And we're going to say same scenario, same stick, same mass, same length. But now we're going to rotate it about this far endpoint. Rotate it about here. Now it's looking more like this. Ooh. That feels a lot more resistance change motion. This is more difficult. Oh. All right, so let's say I equals I naught plus md squared. Isn't that what we just said? Okay. Now, what do I put in for I naught? Yeah, 1/12 ml squared. All right, and okay, I guess this mass is still this mass, so that's the same m. Okay. What do I put in for d? Guys, what's this offset distance?
1/2 L.
Aha! 1/2 L. It's all over 2. Now it's being squared, right? Right. Guys, what is 1/2 squared?
1/4.
1/4? Right. Now, in terms of 12ths, I have 1/12 ml squared here. 1/4. Is that okay if I call it 3/12? Is that okay? Is that the same thing? All right. Now put this together. Guys, what's 3/12 plus 1/12?
4/12.
4/12? And what is 4/12 reduced to? 1/3. Which is exactly what that other table value showed. Right? Yeah, see, if you know one of those values, and you know parallel axis theorem, you can get the other one. Okay? You guys do that? Alright. Alright, go back to the last slide. There it is. 1/12, 1/3. Okay. Alright, pork time. So using that wrench to turn that nut. How much of this can you write in your notes? Like what goes right here? Torque equals what? Oh, actually before that, I've got these components. What is this component right here? It's F times what? Yeah, you guys said sine theta because this component is opposite of the single. Right? Yes, notice the angle I'm giving you is the angle between the vectors, between the r vector and the f vector. Okay. Guys, what if you were given this angle instead from the perpendicular? This would no longer be sine. This would be what? Cosine? Okay, so watch for that. You could see something like that, right? Right, but traditionally, given this angle, this is sine. Okay? So you guys said torque is r cross f. Yeah, it's straight off the AP equations, but that one's good to know anyway. Or how about this box all the way at the bottom? Can you spell that out in terms of theta? This is what in terms of theta?
R
R of sine theta, right? The magnitude of r, the magnitude of f, and then sine of the angle between them. It's the same thing. That's what the cross product is. You're multiplying the perpendicular components. Okay, then all right, now that's for just some nominal torque, right? But what if you consider all the possible torques? Like maybe you subtract out the frictional torque on the nut or right? And you get a net torque. Because if you have a net torque, this could be equal to what? I alpha. Ah, there's Newton's second law of motion in an angular sense. Tau equals I alpha. It's like F equals ma.
Read this stuff.
All right, guys, go with that slide. Go with that slide. It's good. All right, I don't think AP's doing right hand rule. I think they're just doing clockwise, counterclockwise. But if you go to college, you're gonna see right hand rule. Okay. So, guys, right hand rule. You open up the third dimension. You guys see that thumb is pointing along the z-axis. You got RF in the XY plane, and tau is on the z-axis. Right. So this is prep for college right here. And so it's a more mathematically proper way to consider torque. Instead of saying clockwise, counterclockwise, he says it like positive or negative, right? And then, okay, same thing. AP is not going to make you do this giant cross product. Right? Have you guys seen matrices in a math class? Maybe. Show hands. How many of you guys have seen a matrix in a math class like that? Matrix. Okay, like four of you guys. Okay. Yeah. All right. So in college, just be prepared to do something like that. But not for the AP exam.
You teach me how to go left, right, right.
Ooh, is every one of those right there is going to rotate which way?
That way.
Clockwise?
Yeah, that way.
Yeah, again, AP tends to just stick to clockwise, counterclockwise. Those sounds right. Right. But the disadvantage of clockwise, counterclockwise is you have to have a certain perspective in the room. Because what if you walked around to the other side, like walk behind the screen, when you say the opposite? Okay. All right. Ooh, this one right here. You guys remember this lab? PVC pipe, all set. Right. Okay, so here, recap this. So I was taking different lab weights. I was hanging on the string that was wrapped around the center axis, and I was just releasing it from rest, and it was falling. You guys, as this weight was falling, was it accelerating? Yeah, it was accelerating very, very slowly. It was hard to tell with just your eyes, right? But if you did the calculation, say like how far could it fall in some time with the stopwatch, you could show it was accelerating. And the heavier weight you put on there, the more it would accelerate. Okay? And ultimately, we were able to figure out the rotational inertia of this entire pipe system relative to about the central vertical axis. Okay? Now, do you guys see this very last direction right here? It says graph tau versus alpha. That's torque versus angular acceleration. Okay. So I have an animation on the slide. It's going to pop up right here. It just fits. It just fits. But I want you guys to draw it in your notes first. Do a notes check. Walk around the room. Do you guys remember what that graph looks like from your lab? You guys are drawing that graph in your notes. Who remembers how to draw that graph? What was the end result? You know AP loves graphs. And if they have you guys do an experimental design, there's going to be a graph involved. Can you take the equations that you know and interpret them in graphical form? All right, Nicholas got it. This close got this. Dominic got it. All right, but it made over here. All right, you guys get this? Working on it. Working on it. All right, how about check the side of the room one more time? I think. Alex got it. Billy got it.
Oh, it was that guy.
Right, Nathaniel got it. Look, got it. Logan got it. All right. We're getting some winners. Okay. So, all right, here's my version here. Okay. So, guys, tau versus alpha. Now, guys, if there was no friction, more often than not, you guys know AP tends to get rid of friction, right? Like, I should say friction about like inside the axle itself. Right? If that was true, wouldn't this go straight through the origin? It'd be tau equals I alpha, right? Hey guys, what does the slope of this represent?
I.
Yeah, I, the rotational inertia.
Figure that
Right.
out.
Now, why is this graph offset? Why does this have a y-intercept? What does this y-intercept represent? Yes, the minimum torque to get it going, you could say, right? There's some frictional torque that's realistically between these pipes on this axle system, right? And this y-intercept represents that frictional torque that you have to overcome to get it to go. Yeah, it's good to see that. The slope is still equal to capital I, rotational inertia. Right? All right, you guys good with that lab? It's a pretty good lab to know. Pretty good, good. Oh, and there you go. There's I. There's I right there. All right, everybody got that? Forgot about that last animation. Everybody got that? Slope is I. Oh, and there you go. That's that. All kind of things. All right, equilibrium. Now, so guys, for this exam, it's coming up in a few weeks. You probably just have to know two-dimensional equilibrium. Because there's 3 conditions for two-dimensional equilibrium. What, and what?
The X, Y, then the X, Y.
Okay, yeah, something zeroing out. If we see equilibrium, something is summing to 0. What, and also what is summing to 0?
The forces of X 0, some of the forces of Y 0.
Uh-huh.
And then some of the forces of Z 0.
And the torque.
Torque 0.
Yeah, because the forces have to sum to 0 along each axis, and if it's 2 dimensions, it's just x-axis, y-axis. Okay? The torque also sums to 0. Now I put the subscript z, because if you're thinking like in terms of right-hand rule, right, in college you might see it that way. Right? In this class, you can just say that the clockwise torque or the counterclockwise torque has to sum to 0 in the xy plane. Right? Okay, now if you're going engineering in college, you take a whole statics class, you have to take this principle to 3 dimensions. You guys, in 3 dimensions, what do you think this looks like? Yeah, x, y, and z go to 0, and the torque could also be there you go, the xy plane, the xz plane, or the yz plane. Okay. All right. You guys got equilibrium conditions because you're about to have to apply those coming up pretty soon. You guys ready to be applying these? Okay. Force diagram. So we're looking at the forces and the locations of those forces. So guys, if APA ever says free body diagram, you can put all the forces at the center of mass, right? And maybe moments, but I never have you guys draw moments, right? But if they say force diagram, we're looking at specific locations of those forces on the object. Okay, so you may have like a whole bar, like this whole scaffold, and there's different forces at different locations. Right? This ball rolling down, this wrench being turned, there's different locations of different forces. Right? All right, so let's start with the seesaw. You and a friend hop on a seesaw and have this balanced, hence equilibrium. Right? I shouldn't have given you guys the forces, but do you guys see? Well, here, how about this, guys? If this guy on the left weighs 10 pounds, and this guy on the right weighs 30 pounds, do you guys see that? 10 pounds here, 30 pounds here. What is the support force from the pivot point?
40.
40. Yeah, because it has to hold up all the weight, right? So 10 here, 30 here, has to be 40 up there. And I'm still ignoring the lever itself, right? Right. What do you think could go in each one of those boxes for that specific example? Hey, go ahead, in your notes, right? What do you think goes in those boxes? What do you think goes in those green boxes right there? For that scenario. What could you say? Right. A lot of times you'd be solving for something. Because in class, I think we've done this at least a couple of times, is I might have some unknown weight or some weight that's unknown value. And so I'll set up a ruler or a meter stick, I'll balance it, say at the midway point. Then I'll take the known weight, like, okay, well, I know this one's 100 grams, put that over here. And I take my unknown weight, slide it around until it naturally balances equilibrium. And there was enough information there where I can solve this. You know, guys, could you theoretically pick any point in the whole system? And what does the torque have to sum to? 0? I think that's what goes in this box here. Yeah. So sum of torque goes to 0. Guys, this is your main condition. No, it's not the only condition. Really, don't the forces also sum to 0? But we went over that already. Okay. Now, guys, probably like 19 times out of 20, which point do you want to pick as the quote-unquote pivot point to sum the torque about? Yeah, how about this triangle right here? Because usually you know one of these weights, but not the other weight. And by picking this point as the pivot point, like the door hinge, what's the torque caused by the normal force at that very point? 0. So it goes out of the equation, right? Okay, so it goes out of the equation. Right. And then you could create an equation like that. And then if you didn't know one of those weights, you could solve for it. Okay. That's a pretty common application, pretty classic application of that. Okay. So if you have that in your notes, then awesome. And if not, then you're writing that down. So put that in your notes. Always write that in your notes. All right. You guys can solve the seesaw. Solve the seesaw. All right. While you guys are finishing, write that. Okay. Just to reiterate this, I'm going to treat this pivot point as the door hinge. Yeah, mathematically you don't have to, but it definitely simplifies it. And it looks like the small weight on the left side is causing a counterclockwise torque. And then also relative to this pivot point, this big weight on the right side is causing a clockwise torque. Okay, and this one on the right side is 3 times the weight, but it's 1/3 the distance from the pivot point. Hence, the torques zero out. There's zero net torque. Zero net torque. Right. All right, scaffold. Ooh. Scaffold. You guys were hanging a meter stick from 2 spring scales like that, just like the picture showing. Then maybe you hang a weight somewhere in the middle. Okay, what do you think goes in those boxes? Or any of that? Give you guys the picture. Oh, can you draw the force diagram? Guys, can you draw a force diagram that would apply to that picture? Go ahead. Draw that picture in your notes. Draw all the relevant forces. It's just hanging there. It's hanging vertical. Someone's holding on to the spring scales. Can you draw all the relevant forces? And to make it extra fun, let's say that beam itself, that scaffold, that green scaffold, you guys see that green scaffold beam? Let's say that has some weight too. Has a little bit of weight also. Okay? When you guys actually did the slab, you did have to consider, well, the meter stick does have some weight. And it was non-negligible. You did have to consider it. Like if you're hanging on like a 500-gram lab weight, well, the meter stick does weigh some significant amount that I do have to consider. All right. Did you guys come up with these forces right here? And I'll call this the tension on the left side, the tension on the right side, the weight of the beam, and the weight of this lab weight right here. Something like that. Some version of that. Now, guys, in this picture, which tension is greater? The left tension or the right tension? Yeah, definitely the right tension. Because it looks like this weight is closer to the right side. So this right tension has to hold up most of the weight. So there's your 2 conditions. The sum of the forces goes to 0, and the sum of the torque goes to 0. So fill in the rest of those boxes if you haven't yet already. So one condition is sum of forces goes to 0. What's an equation you could craft that could represent that condition? And then that bottom box, the sum of the torque goes to 0. What's an equation? And there might be multiple correct answers for that bottom box, actually. Okay. So that top box is kind of only one way to write it. But that bottom box, there's multiple correct answers you could write. There's multiple correct ways to get the bottom box. So you can write at least one way to write it. I think if I remember right, the way I put it on the slide is I picked this leftmost point as the pivot point. Okay? So that could be useful if, say, you know the weight that you're hanging on, but you don't know the tensions in the spring scale, so you're trying to calculate the tensions. If you pick one point, like this far left point is the pivot point. Yeah, this left tension causes no torque about itself. So you get rid of that in the equation, and then you can very simply solve for the right side tension. Okay, so there's your forces equilibrium. I show hands. How many guys correctly got that forces equilibrium? Yeah, 2 forces up, 2 forces down. They have to zero out. Boom, boom. Okay. How about torque? And this torque equation, again, if you want to make it look exactly like what's about to pop up on the screen, then pick this leftmost point as the pivot point and point to it with my cursor right there. Pick that point as the pivot point. And then sum all the torques about that. So relative to that point, looks like the left side tension, of course, causes zero torque about itself. I think the weight of the beam and that lab weight are both causing a clockwise torque. They're each causing a clockwise torque. And I think that rightmost tension from that right spring scale is causing a counterclockwise torque. And what is the sum of all the torque equal to? 0. Okay. While you guys are finishing writing that, I'm going to set up a numerical example with this one. This is good. We want to throw some numbers with. Alright, so you guys finished it right that. Set some numbers over here. Alright, there's the answer. Alright, so R cross F. I think I got that backwards. It did force and distance, but whatever. It comes out the same thing. Okay, so there's zero torque caused by the left one about itself. Then the beam is at L/2 from the left. Because center of mass of the beam is at its geometric center if it's a uniform beam. Then this weight is at some distance x, which is labeled up here. And this right tension, this right spring scale, is all the way at distance L away from the pivot point on the left. Okay? Those all have to sum to 0. It's for 0 torque.
You said the upward thrust is the same.
All right, you guys got that? Got it? All right, let's do a numerical example. Let's say this beam right here weighs 1 Newton, which I think is pretty close to your meter stick. I think your meter stick weighed about 1 Newton. Okay? And then I'm going to hang on this lab weight. Let's have this weigh, how about 5 Newtons? Let's do that. And let's put this at, well, you know, my picture is showing about relative to the left point. Guys, could that be 75 centimeters? So that was about 75 centimeters. Okay. Now let's put this over here at 50 centimeters. 50 centimeters. Okay. And what I want to know is what's the force in each one of these spring scales? What's the force in this spring scale? I'll call it F left. What's the force in this spring scale? I'll call it F right. Okay. You guys get that? You guys, what did the two forces have to add up to? 6. 6 newtons. 6 newtons up to balance the 6 newtons down. I say, well, I know the sum of forces in the y direction goes to 0 newtons. Therefore, force left plus force right must be 6 newtons. Okay. So, a little shortcut math right here. But you guys can see that, right? Because these two up, and then the 1 and the 5 down, that has the 0 out. Therefore, these two up have to add up to 6. Okay. Now I'm going to pick this far left point as my pivot point. Again, don't have to, but it's going to make the math probably about as nice as it could be. That's your pivot point. The sum of the torque goes to 0 Newton meters. So the unit for torque, Newton meters. Or Newton centimeters, maybe we got 50. Okay. And it looks like the weight of the meter stick itself says, let's go clockwise. And this lab weight says, let's go really clockwise. It's heavier, it's also further out. And this right spring scale is holding everything back in check counterclockwise. So let's go, of course, torque equals R cross F. Right, there's our guiding equation there. So at 50 centimeters, we got 1 Newton weight. That's clockwise. Oops. I'm going to call clockwise negative. You usually call clockwise negative, so I'll just go ahead and do it. Okay. I'll say minus this other clockwise torque. So at 75 centimeters, I got 5 newtons. Right, then I'll say plus for this counterclockwise. It's at 100 centimeters out. And that's some force on the right side that we're solving for. That has to go to 0 Newton meters. 0 Newton centimeters. All right, you guys go ahead and solve that. I'll solve it. You solve it. See if we're getting the same thing here. All right. What are you guys getting for the force on the right side? 4.25 newtons. That's what I'm getting too.
Yeah.
And how do you get the left side force? Yeah, that's the fastest way. Subtract it from 6. That's what I circled up here. So 6 minus that. Look at that, 1.75 newtons. Okay, so there's the answer. There's the left side force and the right side force to hold that up. Yeah, it's about right. All right. All right, you guys can do that. You guys can solve the scaffold. Got your notes.
That's what I was like.
All right. You guys, of course, had lab on the seesaw. And there's a lab on the scaffold. All right, so all labs you can dig up if you want to see some numbers. Ooh, here's a classic question. Ladder rests against a frictionless wall. I think a question I like to ask with this is what's the minimum coefficient of friction with the floor? You guys remember that? Okay. But if you can come up with the equations of how to solve it, then everything else is going to fall in place regardless of what the question is. So this ladder has some length. You can make it length L, and let's say it's a uniform ladder, so its center mass is at the midway point. It's at some angle from the floor. Ooh, that's an angle from the floor right there.
Wait, no, this one or this one's filled.
So whatever theta pops up in the equation, it's relative to the floor. Okay, so here's your conditions. The x-axis forces go 0, the y-axis force goes 0, and the torque sums to 0. Okay. Guys, go ahead and draw a force diagram on that ladder. What's the force diagram? What are all the forces playing on that ladder? Force diagram.
Wait.
You guys drawing a force diagram for that ladder. All right, what forces did you guys come up with?
Weight down.
Yeah, there's the weight down. It's the normal force from the floor. Normal from the wall. Friction from the floor. Okay. Now, I'm not including friction from the wall because I specify there's a frictionless wall. Right, that's a simplification. Otherwise, it gets more complicated. Right. That's a common simplification for this one. Okay, and again, a good question to be looking for is what's the minimum coefficient of friction to make sure the ladder doesn't slide. Okay, but I think what goes in this green box is the equation that you could set up to eventually solve that. And so, what do you think goes in that green box? Go ahead, use your imagination, and write on your paper, write in your notes. What equation do you think could eventually solve that? Probably some torque equation, I'm thinking.
Oh, it's a really long one, but I don't remember.
Yeah, guys, there's some torque equation.
I know.
Okay, if you're gonna set up a torque equation and you're looking for a candidate pivot point, okay, well, I know if I take a pivot point where there's a force at, that force causes zero torque about that very point, right? Kind of like if I press on these door hinges, it'll never open the door. Okay, that one. So with that in mind, do you guys see a really opportune pivot point?
That one.
Yeah. How about that bottom left point? Because there's two forces. Ooh. No, he's pressing on the door hinge. I'm pretty sure that's how I would have set up this torque equation myself. All right, you guys ready? You guys ready? Boom. So mg at L over 2 cosine theta. Here's your lever arm right here. Because we do have to do a torque with the lever arm and right. But notice this is cosine and not sine because it's this angle relative to the floor. So here's your lever arm. I'm tracing out with my mouse cursor right there. And that is L over 2 cosine theta. And then mg, we got that torque. Okay. So this first bit is saying, this first term is saying, let's go clockwise. Make the whole ladder fall clockwise. Okay. Now what's holding it in check, again, from this pivot point, is this normal force from the wall. That's at L sine theta. So here's the lever arm I'm tracing out with my mouse cursor now. Here's L sine theta. So don't those two torques have to sum to 0? Two torques sum to 0. Okay. All right, you guys good on the ladder? You guys good? Good on the ladder. Ooh, cable holds a horizontal bar in equilibrium. Equilibrium. There's another classic question. Hey, is this a lot like the scaffold question?
Yeah.
Guys, I think this is a scaffold question, except that one of your forces is on an angle now. Okay, so if you look back to your notes from a few minutes ago, look at that scaffold. I bet you can use that as a model. We say, well, now how do I incorporate that angle theta? And notice that's the angle relative to the bar, relative to the horizontal. You could possibly be given the opposite, your relative
Tension.
Go ahead, use your imagination. What equation do you think goes in that green box to describe that situation? There's a good chance you're going to be asked this on May 6th. What does this equation look like? Who's trying to get it?
I could get it. I don't get it right here. We'll see.
Who's gonna figure it out?
I think Justin figured it out.
Alright, Justin got it. Yeah.
You just do long plays that are
And so we got working on it. Oh, I gotta get this. You're close there. Close. And some of you guys are real close. Once you guys get this.
No.
Guys, if you can get this one, then you kind of have everything we've done so far with Torque for free, because this definitely covers everything we've done with Torque so far.
What?
If you can get this, you pretty well mastered Torque for a static situation. Take one more trip around the room. I really want where do you guys get this? Alright, Lily got it. Alright, Chloe got it. Yeah. Logan got it. All right, yeah, you guys get this now. Oh, that's what you're about to get it.
I'm excited to sign them. I'm Justin.
If anybody else think they got it, I'm not messing with it, am I? All right, guys, here's the answer. Oh, well, over. We got diagram first. Actually, maybe that's helpful. Guys, if you didn't get it before, then you'll get it now. Okay, take one more shot. Well, okay, there's the force diagram. Here's all the force, all the relevant forces, the relevant locations. Guess I'm gonna take this point as the pivot point. Alright, there's the answer. So guys, relative to this pivot point, at L over 2 is the weight of this beam pulling down. So at L over 2 is mg. Then at the full length of the beam is this cable. So there's the full length L, there's the tension in the cable, right? But one more catch is that we got this angle theta. Right? Now should it be sine or cosine? Well, I think only the vertical component of the tension would actually be holding it up. The horizontal component doesn't cause any torque, but the vertical does. So that has to be sine. Okay? So there's two torques, and they have to sum to 0. Guess that. There's a clockwise torque, there's a counterclockwise torque, they zero out. Okay, you guys can do that? Okay, so everybody gets that? Everybody gets that?
Oh.
I'm gonna find out. Hey! It's the same thing, except with another weight. Aha!
I got this.
Well, if you got the last one, you gotta get this one.
I feel like writing the exam. I was just editing my last exam. You subtract. Hold on, let me write.
Last one we have time for today. This is the last one we're doing today. We'll just continue these slides tomorrow.
Yes. Yeah, I'm gonna thank you. Right, thank you very much.
Let's still call the length of the beam L. All that. It didn't have very good space to write that.
Okay, wait. Yeah, just click.
Alright, there's the answer. Here's the answer. Alright, so get that in your notes. Oh, actually, that's a really good pause point because I see the next slide on my side. The next slide is rotational dynamics with a turntable and a string wrapped around it. Yada yada. Okay, let me show you guys. You guys remember that right there? Okay. So tomorrow we're gonna put things in motion. Do you guys notice today nothing's really been in motion very much? Everything's been static. Okay. But not that. That right there is gonna be in motion. So tomorrow
There's electromagnet.
we'll put this in motion.